Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the OCR A-Level Chemistry A June 2019 paper, so let's get started. In the diagrams below, each box represents an orbital and each electron is shown as an arrow, which one shows the correct arrangement of electrons in an atom of carbon. So if I look at the periodic table real quick, so quick shortcut is that that's the P block, right? Now the period tells you the outermost shell, so period 1, period 2. So I know that this is going to be, this is in the P block, so it's P1, P2, P3, P4, P5, P6, right? And I know it's in period 2, so I know it's going to be P1, P2, so it's going to end into P2. So whichever one of these has 2P2 in it, right? So that's narrowed it down immediately. Well, that's 2P1, 2, 3, so that's out. 2P3 is out as well. So we're stuck with C and D. Now, all orbitals fill up singly before they share. So that's out, so it's got to be D. So which statement about the reactions of halogens with halide ions is correct? So halogen is an element, remember. Halide is that they've got an electron, they've gained it, right? So the general rule of thumb is FCl, Br, I. This can displace this can displace this, can displace this, but you can't go back up. So if I have Cl minuses, F2 can swap for those, right? But so that means if this is swapping for the Cl minuses, then you're going to start with Cl minus, you're going to become Cl2. So what's being replaced is becoming oxidized, but in turn what's replacing it is becoming reduced. That's what it is. And down the group it happens less because the electron shells are getting higher in number, so the nucleus is attracting those electrons less strongly. So here we just need to look at which options we have and which one adds up, so one by one them. So I2 can oxidize Br minus. It can't. You can't have iodine oxidizing it because it's less, it's got less oxidizing power, so that one's out. Now number 2, if we look here, it says, if we look at B, Cl2 aqueous can reduce Br. It's not that, because if Cl2 were to reduce Br, then you would get like Br2 minus. Remember that this Br is getting swapped because it's becoming oxidized, and then the Cl is getting reduced, so that one's out. Then it says Br minus can reduce Cl2, so Br minus Cl2. Now this is the reverse in itself. It's tricking you here. This is very cheeky, right? Because if you think about it, the Cl2 displacing the Br like it would be, so if you had Br minus, if it's displaced, you end up becoming Br2, which means it's lost electrons, right? The Cl2 has become Cl minus, which has gained electrons. So this is actually correct. This Br minus gets displaced by this by reducing this and becoming oxidized itself, which is very cheeky. And then Cl minus can oxidize I2. Well, no, because if Cl minus is already has done the displacing part. If it was to oxidize I2, you would end up getting I plus something, which doesn't add up, so that's out. Next it says one molecule of the gas has a mass of this. What's the possible formula of the gas? So one molecule in its entirety is 2.658 times 10 to the minus 23 grams. All of your periodic table masses are in grams per mole because it's telling you that one, like for example, if you look at carbon, it has a mass of 12. It's telling you 12 grams per mole, which means 1 mole weighs 12 grams. So if here 1 mole of these weighs 12 grams, then that means that one singular one has to be, one singular atom, right? 1 mole is Avogadro's constant. If I have 1 mole of bananas, I've got 6.02 times 10 to the 23 bananas. We only have one molecule here, right? But we now, all the periodic table numbers and MRs are in moles. So then if one molecule has a mass of 2.658 times 10 to the minus 23 of them, 23 grams, then 2 molecules would be double that. So then Avogadro, 1 mole of it, would be this times Avogadro's, this times the Avogadro constant. So if I do that, I will get 160016. So that's its MR. So it's got to be something with an MR of 16. And the only one that is A. And there you go. That's how you do that. So in the laboratory, acid spills can be cleaned up and made safe by spreading anhydrous sodium carbonate to neutralize the acid. A student accidentally spills this much on a bench. What's the minimum mass of this? So quickly sketch out what's happening. Sodium carbonate is Na2CO3, right? And we're adding HCl. If we're going to neutralize this, then we're going to need 2 moles of HCl for every one of these because, CO3 2 minus, Cl minus, right? I don't even care about the rest. All I need is that. Now, to work out the mass, they've given us the concentration and volume, so I can work out the moles of the HCl that they would need, which is going to be 2 times 50 over 1,000. If I do that, 2 times 50 over 1,000, you get 0.1 moles. You can see it's a 2 to 1 ratio, so the moles of the Na2CO3 we need is going to be a half of that, which is going to be 0.05, right? So then the mass we need of this thing is going to be its moles times its MR, which is going to be 0.05 times its MR, which is 106. And if I do that, I get 5.3 grams, which makes it B. So now it says, what's the oxidation number of N in MgNO3.H3H2O, right? So the bit that we really give a damn about is this here, MgNO2, sorry, whoops. So Mg is an Mg2 plus here. This NO2, there's two lots of them, so each NO2 has to have an overall charge of 1 minus. That means you can look at the oxidation states, because oxygen's always really 2, right? And there's two lots of it. So 2 lots of minus 2, plus whatever the oxidation state of nitrogen gives you minus 1. So X plus minus 4, or X minus 4, gives you minus 1. So that means that the oxidation state of this has got to be plus 3. So that makes 5B. There you go. Which one of these is a redox reaction? So you just got to rapid fire look through them and see what's up. So Na stays as Na plus, and Ag stays as Ag plus. So that one's immediately out. Next, Na plus, Cl, Cl minus, NO2, NO2, exactly the same. So that one's out as well. Next, Ca2 plus still is Ca2 plus. HCl, Cl minus is still Cl minus. H and H, these are still all 1 pluses. You should be able to kind of just quick fire look at them here. However, CuO, that's plus 2 minus 2, right? And we've got elemental Cu, so that means by default already we've had reduction of this because it's gone from Cu2 plus, or plus 2 to 0. So that means where you've got oxidation, something else has to be reduced, no matter what. The half equations to do are redox half equations, where one is oxidized, one's reduced, but these are overall equations. So by default, for the fact that something's being oxidized here means the other thing has to be reduced in anyway. But if we look here, we've got NH3 and then we've got N2. So now you need to decide, we know that the oxidation state of that is going to be 0, right? But we've got NH3, NH2O. Now it's hard to decide which one's the oxidation number of what. Now N is more electronegative, which means this one's going to be the negative-y one, right? So that means the oxidation state of this is going to be minus 3 and that's got to be plus 3. So then that means if it's going from minus 3 to 0, it's lost electrons, right? So that's been oxidized. So that's what gives you D. General rule of thumb is if you're stuck between what's being oxidized and reduced in things like NH3 and stuff, the more electronegative thing is going to be the negative E oxidation. So then it says, which elements of the solid state contain a simple molecular lattice, a giant covalent lattice, and a giant metallic lattice? So simple molecules are just things that are covalently bonded to each other, but they're separate molecules. Like I2, for example, is I bonded to I, and then another I bonded to I separately from it, right? It can be as much as you want. So the sulfur would be, so sulfur normally exists as S8. That's a simple molecule. I know there's 8 of them, but that's a simple molecule. And then giant covalent lattice, silicon can form that. And aluminium is a metal, so it's got to be A. Immediately. There you go. Because if we look here, that's a simple molecule. Yes, that's a giant covalent lattice, but that's not metal. That's a simple molecule. That's a simple molecule. That's a giant covalent lattice. That's a metal. That's a simple molecule. That's a simple molecule. So therefore, it has to be 7A. 3.528 grams of a group 2 metal is reacted with an excess of chlorine, and then you make this much chloride. What is the metal? So this mysterious metal, which is group 2 plus Cl2, gives you M, and then something, Cl2, right? So then we know that there's this much of a chloride, and we know there's this much of this, and we've reacted with excess chlorine. So then here, the moles of the M, this mysterious metal, is going to be its mole mass over its MR, which is going to be 3.528 over the MR, which we don't know what it is, right? Now, the MCl2, they've told you the moles of this mysterious metal is going to be 9.775 over the MR of this thing, which is going to be MR plus 2 times the MR of the Cls, right? Plus 32 times 35.5. Okay, cool. Now, they're in a 1-to-1 ratio here, so that means that this has to equal this. So 3.528 over MR, this mysterious MR has to be 35.5 over the MR plus 35.5. If I times both sides by this, that'll bring that up here, and if I times both sides by that, that'll bring that up there. So then it means that 3.528 MR plus 3.528 times 2 times 35.5 equals 9.775 MR. So if I tidy this up, I get 3.528 MR plus 250.489 equals 9.775 MR. So move all my MRs to one side. So that means that 250.489 equals, so collecting alike terms, remember, 6.247 times this mysterious MR. So then this mysterious MR has got to be 250.489 divided by 6.247, which gives us 40.09, which is roughly 40.1. So that means whichever one of these is 40.1 on the periodic table is this mysterious metal. So that's got to be calcium. There you go. So you've got to just use the facts in the question and work backwards, right? Like, because to identify this metal, we're eventually going to have to boil it down to its MR. So I just thought immediately the moles of this is going to have to be the moles of this. And I know that the MR of this is whatever. The MR of this is just 2 Cls added on. There you go. It says, which statement is not correct about group 2 hydroxides? MgOH2 can be used to treat indigestion. That is true. So That is, that's not the one that's incorrect. CaOH2 is used in agriculture to neutralize alkaline soils. No, because the reason they do it is to increase the pH of it. And this is an alkaline solution, so why would it neutralize an alkaline soil? For it to neutralize that, it's got to be acidic itself, which is incorrect, so it's B. There you go. Next it says radical reactions are responsible for the catalyzed breakdown of the ozone layer. The overall equation is shown below. Here it is. And then it says the molar gas volume of this is about that. What is the energy released in this during the breakdown of this in the ozone layer? So look at the units. It's told you that the molar gas volume is that every mole of this has a volume of that. That's what the per mole means. So 1 mole is going to be 2.5 meters cubed. So that means 2 moles would equal, 2 times 2.5 meters cubed, right? So if the question's told you that you've got 1 meter cubed of this, right? It's going to be x times this mysterious thing, then that means x moles of this is going to be that, right? So then they've told you that we have 1 meter cubed of this mysterious thing, right? So we can see that 2 moles is 2 times this thing, right? So x moles, the mysterious number, is going to be x times the 2.5, right? So then we can say that x times 2.5 equals 1 meter cubed. So therefore x, the number of moles we want, is going to be 1 over 2.5, which is 0.4 moles. Now they've told you in the question that, what is it? They want to know what the energy release is this. So they told you the enthalpy of this reaction over here is minus 284 kilojoules per mole. So that means 1 mole releases this much, right? So in that case, if 1 mole releases minus 284, then, like I said before, 2 moles would be 2 times minus 284. So that means here we've got 0.4 moles, which means it's going to be 0.4 times 284 minus that, which is going to be times minus 284. It gives you 113.6, minus 113.6. But the thing is that this is per mole of this. We have 2. So that means we have to divide it by 2, because where the moles that we have is double the amount here, if that makes sense, because every mole of this makes this. But I've slapped in this number, which represents 2 moles. So that means if you divide that by 2, you then get an answer of minus 56.8. And this is the energy released, so you don't have to keep the minus in, because the minus tells you it's that's its A. So now it says there's a graph of ln k against 1 over t, and it has a gradient of this. What's the activation energy of this, right? So every single straight line in the universe represents this. Y equals mx plus c, where y is your y coordinate, m is the gradient, x is your whatever x coordinate, and this is your y intercept. So what you do is you just look at what they've told you in the question and what's become what. The y has now become ln k, right? And your x has become 1 over t. We still have something times this, your gradient, plus c. The formula that you know and are given is ln k equals minus ea over rt plus ln a. All you do is you compare this to this and see what the missing parts are. ln k and ln k are the same here. We have 1 over t here, but here we have minus ea over r. Side by side, if we're comparing that means that the m has to be minus ea over r. Because if you times that by 1 over t, you get this. And the minus bit as well, because remember that this y and x plus c bit is positive. So that means the m is this. And also, if you want to go further, whatever's left over, the plus c plus ln a, right? So they've told us that this gradient is minus 4420, which is minus ea over r. So that means that if we times both sides by r, which is 8.31, then you would get minus ea is equal to minus 4420 times 8.31. And you can flip the signs as well. So ea would be this, but the other sign. So if I do that, I get 36730.2, right? And it's positive. However, the equations, all of them work in joules per mole, and this is asking for kilojoules per mole, so we have to divide it by 1,000, so it's actually that, 367.3. So by that, it's got to be C. There you go. Next it says the equation shows the dissolution of this acid, H3ASO4, in water, which pair is a conjugate acid in a base pair. So anything in the universe that puts out an H+, as it loses it, is an acid. Anything in the universe that reacts with an H+, no matter what. It doesn't matter what it is. It's nothing to do with its charge. It's nothing to do with literally anything. According to the Bronsted-Lowry model, anything in the universe that puts out an H+ is an acid. Anything that takes it is a base. Because I see a lot of people say, oh, but it's charged at this and that. That's why it's not. It's like, no, it's not. If I have, for example, NH3 plus H+ going to NH4+, anything that's lost this is an acid. Right? Anything that's gained that. People love saying proton donor and proton acceptor, but I have no clue what that actually means. If we look here, this NH4+ has lost an H+ to become this. So that is an acid. This can gain an H+ to become this. So that's a base. So what we need to do is we need to look out for what's lost the H+ and what's, gained it. Right? So here, H3ASO4 to this, this has to be an acid because it has lost an H plus to become that. This can gain an H plus to become this again, so that's going to be a base. And then here, that's gained an H plus, this is lost one, so that's going to be your other acid, and that's going to be a base. So whichever one fits with this is the answer. So this and this are no, because this does not lose an H plus to become that, nor does it gain one or whatever, so that's out. This and this, again, same thing, this doesn't lose an H plus to become that, or gain one and so forth, so that's out. This and this, again, same reason, so it's only got to be D. Now it says, what's this number of stereoisomers that this can form? So this is Ni with this thing here. Now remember, with transition metals and ligands, look out for where the lone pairs are, and that'll tell you how many lone, coordinate bonds it can make. There's a lone pair here and a lone pair here. So this is bidentate, right? And then these are Cl minuses. So there's only two. There's only There's only one lone pair each. So that means we can squeeze. This thing has two big bidentates and two Cls on it. So it means, for example, if I were to draw just a really quick sketch of this, rapid fire is going to have this and this like that, right? So then you need to just think of the stereoisomers that it can form. So stereoisomers are mirror images, and also you got to look at cis-trans isomerism. So you can have a so you can have a trans isomer there on the opposite sides, or you can move the Cl there. So immediately you've got two here. However, it can also do optical isomerism as well, because if I have Ni, and then I'm just going to do straight lines, you should do wedges, but if I do Ni, and I've got like Cl, for example, and this, its mirror image is going to be Ni, Cl, and then it's going to be, one sec, this and this, which are mirror images. So based on that alone, we've got one trans isomer, that isn't optically active. We've got two cis isomers here as well that are optically active, so they have stereoisomers. They're optical isomers, so it has to be 3, which is B. So then it says, what properties are correct for a transition element? This one actually makes me want to put a bullet through my head sometimes, low-key. Like, the amount of times I say, what makes a transition metal element? They're like, oh, partially D-filled subshell. Right, but if we look at copper, for example, that's 4s1 3d10. That's a fully filled D subshell. So does that mean copper's not a transition metal? No, because when you make it a Cu2 plus ion, it becomes 4s0 3d9. So it is the ion, so it has stable ions with a partially filled D subshell. Because if we took your logic and said partially filled D subshell, right? Scandium is 4s2 3d1. And the only ion it forms is Sc3+, which is going to be 4s0 3d0, which has an empty D subshell. So it's not a transition metal unless it has stable ions with a partially filled D subshell, so that one's out. Then it says the existence of more than one oxidation state in its compounds. That is correct. That's one of the properties of it, because the electrons can move up and down energy levels and be excited, but they're quite close together, so it's allowed to do that. And then the formation of colored ions as well. So it only is 2 and 3. 1 is not wrong, and the amount of times people jump to saying that actually just, oh my god, pet peeve. Now it says 4 redox reactions relevant to hydrogen oxygen fuel cells are shown below, which is correct for an alkaline hydrogen oxygen fuel cell. Right? Cool. So in an alkaline hydrogen oxygen fuel cell, a hydrogen fuel cell, quickly, is where you've got H2 plus a half O2, 0 overall reaction makes H2O liquid, right? That's overall what it is. Now, whichever one of these is going to give you an overall reaction is that. So if you see the H2 and the O2 and whatever, right? What's happening to the H2 is that the H2 is becoming from 0 to +1, so that's got to be oxidized, so the O2's got to be reduced. So whichever ones fit the bill for this is going to help us figure out what it is. Now it's told you here that this is an alkaline hydrogen oxygen fuel cell, so we can use that to decide what we want. So we need to find out any combination of these where H2 is becoming H+, which is going to be this one, and then oxygen is becoming is being reduced. So our options are where's our oxygen? If it's being reduced, this, or it could be this, right? Because that eventually gives you this. The thing is, though, is it's told you that it is an alkaline fuel cell. So if we've got this and it's being oxidized into this, but we need something that's alkaline that's going to give us H2O eventually, rather than, because if we did this and then also this, yes, admittedly it will give us the H2O we want, but it's not alkaline. There's no OH minuses in it. If it's alkaline, it has to have OH minuses in it. So what happens is that gets oxidized, this gets reduced, you form this, and then they react like this, and they give you the H2O. So whichever one of these fits the bill for that is going to be it. So the reaction of the positive electrode is this. So the positive electrode, remember, is so it's anox red cat, is how I remember it. So reductions at the cathode oxidation is at the anode, right? Now an anion is negative, a cation is positive. So annoyingly, a cathode is your negative electrode, and your anion is your positive electrode. Anode, is a positive electrode. It's what they're attracting rather than, what they are like in that term. So in this case, it's saying what the positive electrode is this. So positive electrode is going to be your anode, which is whatever's being oxidized, which is immediately 1 is out because that's showing you reduction. So, it definitely can't be 1. Next, it says the overall reaction is this. That is correct. And the cell potential is this. So EMF is going to be equals E reduced minus E oxidized. In this case, it's going to be 1.23, which is being reduced, minus what's being oxidized, 0. So it's got to be this one as well. So it's got to be whichever one's 2 and 3, which is C. So you can figure it out like that rather than having to memorize things. Like, the only bit I had to really memorize was just this overall equation, to be honest. Oh my, what a name. So Humphrey Davy discovered several elements including sodium, potassium, magnesium, calcium and strontium. Explain which block in the periodic table sodium and magnesium belong to. So it is the S block because they're both in the first two, things, and they also have electrons in the highest energy of their outer electrons are in an S orbital. So you need to say that as well. So the outer electrons in an S orbital, because that's what it says. Explain which one. So explain means why it's there. It says a sample of magnesium has an AR of this, and it's found to consist of 3 isotopes. The accurate blah 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 and the percentage abundances are in the table. It says to work out the relative isotopic mass, and it says give it to 5 significant figures. So they've given us 2 of these isotopic masses, but they said find out the relative isotopic mass of this third isotope in the sample, and it says give it to 5 significant figures. So we've got something that weighs, has a mass of X. Its relative isotopic mass is going to be X. We don't know what it is, and we know that its percentage abundance. Well, this has to add up to 100, so it's got to be 78.99 plus 10, and then take that away from 100. If we do that, then this mysterious thing has to be 11.01%. Now, the relative atomic mass or isotopic mass or whatever, relative atomic mass is going to be all of these isotopic masses times each other divided by 100, right? So it's going to be 286.06485 equals 11.01x. So then x is just going to be that divided, this divided by the 11.01. So if I do that, I get this divided by 11.01, which gives me 25.9822752, and they want it to 5 significant figures. So 25. It says 1, 2, 3, 4, 5. There you go. A student adds an excess of calcium oxide to water in a test tube, and then they add an excess of strontium oxide. Write the equation for the reaction of calcium oxide with water. So CaO plus H2O is what you definitely know you're going to react, and then you're going to make CaOH2. Suggest the approximate pH of the 2 solutions in this test tube. So if it's calcium oxide, it's going to be greater than 7 because it's going to form an alkaline solution, but less than 14, right? So I'm going to choose, like 10. Strontium is going to have a higher one because it's further down in the group, so it's more soluble because its outermost electrons are further away and so forth. So that means it's going to have a higher, so I'm going to choose 12. Now, you've heard me do this time and time again in every video. If you are doing enthalpy changes and you're doing it any other way than drawing cycles and using those, and if you're trying to use formulas and this plus this, or I don't know, bonds made, bonds broken equals this, you're doing it wrong. Only way to do this is to know the definitions, the moles and the states of everything from what to what, and be able to write them as an equation, and also draw a cycle. Every single arrow is a cycle. If you're doing it any other way, no matter what, who you think you are, you're doing it wrong. I do not care. There is no way of doing it. You'll hear all kinds of garbage on TikTok. I've also seen all kinds of garbage on TikTok and social media. Y'all are doing it so horrendously, embarrassingly wrong. There's only one way to do it, and it is to understand these definitions and use them, and use a bit of logical thinking and common sense. If you're having to complain about memorizing the definitions, you don't know what you're doing. What I mean by that, so here it says formation of potassium oxide, so that means you're making 1 mole of potassium oxide, which is K2O, from its elements in their standard states. You should be able to immediately recognize that, because then you can look at what's starting and what you're finishing with, and then working out the next bits. That's the enthalpy change, because then you can decide what goes in a cycle. This whole topic, you should be only doing it this way. There's anything to do with enthalpy changes, mean bond enthalpy changes, this and that, blah blah blah. So all of it is this. It says here there's an incomplete Born-Haber cycle that can be used to determine the lattice enthalpy of this potassium oxide, and in the boxes below complete the species in this cycle and include state symbols. The reason the state symbol's there is because it tells you what the definition is. It's crucial. You can see we've got solid potassium and O gas. The O gas is unchanged. The solid potassium has now become gaseous 1+. So that means we've done 2 things. You should be able to recognize immediately. We've atomized it to make it gaseous, but also ionization energy did. So the first ionization energy is where you're making 1 mole of gaseous 1+ atoms from gaseous atoms. This is not gaseous. So it must have been turned into gaseous to begin with, which is the enthalpy change of atomization, where you go from 1 mole, where we make 1 mole of gaseous atoms for an element, 1 mole of an element in its standard states. So that means here this has to be 2K gas plus O gas. That's what I mean by knowing these definitions, otherwise it just don't make sense. Now here we can go from something and it forms this 1 mole of K2O. But as well as that, from here you can turn into this. So that means between here and here, there's no ionizationing or anything like that, or electron affinitying, so it's got to be 2K solid is definitely there. Here, O gas does not exist like that. It's half O2 gas instead. So that means that this is going from its elements to 1 mole of a compound, so that's your enthalpy of formation. Whereas here, solid potassium, but half O2 gas, its element becoming gaseous atoms, so that has to be enthalpy of atomization. Then, if we look here, we're going 2K plus and all of this, blah, 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 2E minus, and then eventually we're making something else, and then we're making something else, and then eventually we make a solid ionic compound. So that means that before this, something is going into making the solid ionic compounds, it's got to be these gaseous ions we need. And then in this in-betweeny line, well, we've got 2K plus, and that's still 2K plus. We've got O minus, which is going to O2 minus. So what must have happened was you've done the first electron affinity here. Like that. That's how you do these. Then it says, calculate the lattice enthalpy of potassium oxide. So what you need to do is you look at your cycle and put the numbers in based on what it is. So this is the enthalpy of formation, because we're making 1 mole of a solid ionic compound from its constituent elements in their standard states. So use the table and put the numbers on the cycle for first. So here, that's going to be minus 363. Then we're going from this to this. What's changed is that we're making 1 mole of gaseous atoms from an element in its standard state, so that's the atomization of oxygen, which is going to be 249. Now from here to here, nothing's changed, but from here to here, we are making 2 moles of gaseous potassium ions from 2 moles of gaseous, 2 moles of the potassium in its normal state. The definition says 1 mole, so we're going to have to do 2 of this. So it's going to be 2 lots of 89. Cool. From here to here, we're doing the first ionization energy, which is where you make 1 mole of gaseous 1 plus ions from gaseous atoms. However, we've got 2 again, so it's going to be 2 lots of the first ionization energy, which is 2 times 419. We use 1 mole because the enthalpy changes are all measured in kilojoules per mole, meaning 1 mole of whatever it is will put this much energy out, take it in. We use 1 so we can allow for comparisons and keep it consistent. So whenever you see disparities with that, you've got to account for that. Here, we're doing an electron affinity of oxygen, and it's where you make 1 mole of gaseous 1 minus ions from gaseous atoms, and there's only 1 here and 1 here, so that means we can just stick that in here, so it's minus 141. And this is the second ionization, and it's second electron affinity, which is going to be plus 790. So from here to here, we're making 1 mole of a solid ionic compound from its gaseous ions, meaning that this arrow has to be the lattice enthalpy. Now the rules are that if you start and finish at the same point, the enthalpy change is the same. That's what Hess's law says. So if I start here and I finish here, then that arrow, the enthalpy change, has to equal starting here, going all the way around here, and then eventually down here, because I'm still starting and finishing at the same point. So write that down as you're working out, and then you can do the rest. So that means this arrow, which is minus 363, equals all of these arrows added up. So we're following every other arrow, so it's going to be 249 plus 2 lots of 89 plus 2 lots of 419 minus 141 plus 790, and then plus whatever this enthalpy change is, the lattice enthalpy. Now, simplify it, and then you can find what you need. Do it like this, and you'll always get method marks for your working. So if I tidy this up, I get minus 363 equals 1914 plus the lattice enthalpy of this thing. So then all I do is just rearrange it to go down 1. So the lattice enthalpy of this thing is going to be minus 363 minus that, which gives you minus 2277, and that checks out because it's the lattice enthalpy, which is where you're forming 1 mole of a solid ionic compound from its gaseous ions. And if you're forming bonds, you're making bonds, which is exothermic, whereas endothermic is you're breaking them because you have to put energy in to break it. So there you go. So now it says a similar Born-Haber cycle for potassium oxide can be constructed for sodium oxide. The first ionization energy is more endothermic than that of potassium. So what that's saying is that the K versus Na, your first ionization energy, for some reason for sodium is higher, and this one is lower, right? So if you're having a more positive or higher enthalpy change, that means you're getting more endothermic, which means more energy is absorbed, right? And that means bond breaking, right? Whereas exo is less, right? And it's more negative, and that's energy released, and that's bond making. So it's asking you, why is this more endothermic? Well, if it's more endothermic, it means more energy has been required to, overcome the attraction, because it's the first ionization energy, peeling an electron off, the attraction between the nucleus of sodium and the outermost electron. that's what you can immediately conclude. And then just compare them side by side. The only difference between these two is potassium versus sodium. They're both in group 1. The only difference is that this has more shells. So Na has less shells, therefore the attraction is stronger. That's it. There you go. So it's applying those fundamentals here. That's all of this. That's all it is. Now it says the lattice enthalpy of sodium oxide is more exothermic than that of potassium oxide. So remember I just said exothermic is bond making. So what's happening is there's more energy released here when you're bond making than here, right? So then the only difference, we're comparing the ions here now because we're not dealing with atoms. The difference between here and here, the only difference is that this has less shielding. So Na plus has less shielding, and for some reason this leads to more energy released, you know, when cations and anions bond, when the bonds are made. Then the reason for that must be is that because of that less shielding, the less shielding means that there's got to be more attraction between these ions. You know, these positive and negative ions, and like the oxygen and the Na plus ions. And that's it. So rather than trying to memorize answers or regurgitate model answers, quote unquote, which I can't stand, just look at it and use some common sense. Healthy human blood needs to be maintained at a pH of 7.040 for a body to function normally. Just a side rant, alkaline water and all that garbage is a load of garbage because this does need to stay like this. If it deviates even like, you know, outside of the normal range, you can die. So if you could somehow control it by drinking like, you know, Gwyneth Paltrow goops like alkaline water, like that's a pretty rubbish system because you can die. So I'm just saying. But anyway, carbonic acid H2CO3 is a weak acid in which hydrogen carbonate ions act as a buffer to maintain the pH of blood. The pKa is this. Explain in terms of equilibrium how this mixture acts as a buffer in the control of the blood pH and calculate the ratio in healthy blood. So do it step by step. First of all, write out an equation for this, the equilibrium. Otherwise you're screwed. This is a weak acid, it's told you, so it's going to be H2CO3, and they've told you in the question that it is making HCO3 minus, the other one's got to be H plus, and this is all aqueous, right? But the question's asking how can it act as a buffer in the control of blood pH, which means we're resisting pH changes. So describe it in terms of equilibriums. So if it's acidic, like you know, again more acidic, that means you've got more H plus. Le Chatelier's principle says that an equilibrium wants to counteract any change that is made. So don't just say to counteract the change, say what it is doing. So I literally say increasing H plus means that the equilibrium will shift to counteract the change to decrease the H plus. So I say it there and straight away. And then I say how. So adding, if it's more acidic, I mean you're increasing the H plus, which means the equilibrium shifts to decrease the H plus, and it does this by reacting this, because you want that to go down if it's shifting this way, right? So that means this and this react. So therefore, HCO3 minus and H plus react to form H2CO3. There you go. Now with alkaline scenarios, what's happening is that you're now adding OH minus. So the equilibrium shifts to counteract the change, which is to remove OH minus, right? So in this case, you've got to look at this and say, well, I don't see any OH minuses in this, so I can't really see it very easily. What happens is the OH minus comes along, swoops in, and reacts with the H plus to give you H2O. So then that's what you would say. The OH minus reacts with H plus, and that gives you H2O. But then that's now dropped. So then the H plus drops, right? If the H plus drops, that's how you're changing the equilibrium. So the equilibrium now shifts again to increase H plus, so it shifts to the right, so more H2CO3 dissociates into H plus to make it back to normal. There you go. So now we've talked about that, and it says calculate this in healthy blood. So in healthy blood, they've told you that the pH is 7.40. They've told you that the pKa for this is 6.38. So Ka is going to be 10 to the minus 6.38. Now they've told you to work out the ratio of this to this, right? That's your HA, that's your A minus, right? So if the Ka formula is that, then if I rearrange this to get Ka times HA, that would give me H plus and A minus, right? But then if I divide both sides by Ka, I'll get HA equals H plus A minus over Ka. But then if I then divide both sides by A minus, I'll get what I want. I'll get HA divided by A minus equals H plus over Ka, which is indeed the ratio that they want. So that means it's going to be 10 to the minus, what was the pH? So 10 to the minus 7.4 over the Ka, which is going to be 10 to the minus 6.38. If we do that, we end up getting, it's going to be 3.98 times 10 to the minus 8 over 4.17 times 10 to the minus 7, right? That's HA to A minus. So you can rewrite this ratio as HA to A minus is going to be the same as saying the 3.98 to this, right? So divide by the smallest number for both of them. So I'll rewrite this just at 3.98 times 10 to the minus 8, and then to 4.17 times 10 to the minus 7. The smallest of the two of these is here, so if I divide that, it's going to be 1, 2, whatever that is, divided by the 3.98 stuff. So right, 4.17 times 10 to the minus 7 divided by 3.98 times 10 to the minus 8 gives you 1 to 10.477. There you go. Or 10 to 5 if you want to do 3 significant figures. So we should really do that. So it's 1 to 10.5. There you go. It says red blood cells contain hemoglobin. Explain using ligand substitutions how hemoglobin transports oxygen around the body, and then why carbon monoxide is toxic. So if it's going to be doing, you know, oxygen and taking it around the body, and it's to do with ligand substitutions, the oxygen in the question is telling you that it must be acting as a ligand. So what happens is that oxygen bonds coordinately, because if ligands act via coordinate bonds or datively, to, and then it's remembering what complex, you know, like what metal in the hemoglobin it's doing it with. So the metal it does it in hemoglobin is Fe2+. It forms covalent dative coordinate bonds. Then when it's required, right, you want to get it like away from the hemoglobin, the Fe, sorry, right? So we need to take it off. The only way to take it off is by substituting it for something else. You can't just make it like disappear. So when it's needed, the O2 is substituted for another ligand. The other ligand it is what your body is mostly made of, which is water. So the H2O literally swaps for it and then it's taken off. Or CO2, but H2O is the more, you know, thing, right? Fine. That's pretty much that, right? And then it says, explain why carbon monoxide is toxic. Well, CO forms dative covalent bonds with the Fe2+, but this is stronger and therefore, you know, isn't displaced or substituted. Therefore, hemoglobin can't carry oxygen. There you go. This question is about the reactions of ions and compounds and transition elements. They do something with the solution containing this. They add an excess of aqueous ammonia to this and a purple solution is formed. And then they carry out the following sequence. So they add, this is a separate experiment, so they get NaOH and add it slowly, and then they get a green precipitate, and then they add an excess, and then it dissolves in a green solution containing a 6-coordinate complex ion is formed. Then what they do is they add H2O2, and then it's heated, and a yellow solution is formed, and then the solution in this tube is now acidified, and now they get Cr2O7. So it says, what is the formula of the complex ion of the purple solution that forms? So if they're adding an excess of aqueous ammonia, lots and lots of ammonia, the option, if you're adding ammonia, the options is that it forms a precipitate, where it's usually some metal, a hydroxide, and it's not charged. So like for example here, it'd be CrOH3, H2O3, if it's not charged. Generally when it's not charged in this context, it's solid, right? Now, here it's a purple solution, so it's some sort of solution, and we've added lots and lots and lots of NH3. So it's quite literally that the NH3 is just swapped off entirely all of those waters, like that. Then it says, suggest an equation for the reaction in experiment 2, step 1. So in experiment 2, step 1, put in what you already know. You definitely know that you are reacting this already, no matter what, because they've told you that in the question. So Cr, H2O, 6, 3+, right? We need to think what's it realistically going to be, as it says include state symbols as well as aqueous, right? Now they've told you that they're adding an excess of this, and step 1. They're adding an AOH, and then we get a grey-green precipitate. So we know that the OH minuses are going to be reacted with this. Next, if it's a precipitate, and we're adding OH minuses, we're going to get Cr, OH, and then 3, H2O, 3, like I said before, solid, because there's no charge, and then whatever's left behind, H2O, 3, right? Liquids, 3 of them. So that means we're going to have 3 of these. A lot of people say that this is a ligand substitution reaction. It's not really, because like you can do this with NH3 as well. And in that case, where's the, O's and the H's coming from? The reason this drops around from 6 to 3 is not because 3 of them got swapped with this. It is because they have lost H pluses. Each one has lost an H plus to form this OH. That H plus, so that means that this is acting as an acid. and because it puts out an H plus, every acid in the world puts out H pluses. So if that's the case, then something else has to take it, and that's what this does, is it takes the H plus and makes the water like that. So it's actually that. Now it says, draw a 3D diagram for the shape of the complex that forms in experiment 2, step 2, and then include the charge. So in experiment 2, step 2, what we have made is we have made a precipitate, but we've made that precipitate, but then it dissolves and you get a green solution of a 6-coordinate complex ion. So what's happened is now that we've added so much OH3 that all of these now disappear as well, and now we've just got OHs on its own because they reacted now. So the 3D ion, what you do is you draw the the wedges and the dashes and whatever, like so, right? And then you draw it like lone pair by lone pair. So start with O, H, O, H, O, H, O, H, O, H, and then OH. And you now have a problem with it. So this is 3 plus, this is all 1 minuses, and there's 6 of them. So that means the overall charge is 3 minus. There you go. Next it says, what's the formula of the ion that causes the yellow color in this? So it's got to be, it's the ion, so it doesn't want you to say Na2CrO4, it wants you to say CrO4 2 minus, that's the color. And then it says, what's the color of the solution? So it's the one that makes the, where is it? It's the Cr2O7 2 minus ion, which is orange. So the colors just got memorized, unfortunately. One quick shortcut you can use is by using the periodic table as it's supposed to be, you know? Period 1, period 2, period 3, period 4, period 5, period 6, and so forth, right? This tells you the outermost shell. This is the D block, right? This is the S block, so if I chose, for example, potassium, and it's going to be 4S, and it's S1, S2, 4S1, right? Now here, these aren't 4D, because the 4S fills first, which is where it gets a bit annoying. So that means that 4S fills in all of these cells, so it's going to be 4S something, 3D something, right? So D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. However, copper and chromium are the weird ones in which that likes D10 and that likes D5. But anyways, it's saying V3 plus, right? So D1, D2, D3. Vanadium is 1, 2, 3, so it's D3. So vanadium chilling, blah, 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 is whatever. It's going to be 4S2, 3D3, right? They've told you it's V3 plus. The 4S is filling empty first. So that V3 plus is going to be 4S0, and then, because those two are gone, and then 1 from here, 3D2. So that means it's going to be all the way up to that. So it's going to be 1S2, 2S2, 2P6, 3S2, 3P6, 4S0, 3D2. There you go. Student adds excess ion to a solution containing VO2 plus and observes that the color changes from blue to green and then to violet. They're using the relevant electrode potential shown to explain these observations. So if it's going from, so you've got to use these things here. So if it's blue, that's VO2 plus. If it's green, then it's V3 plus. And if it's violet, it's going to be V2 plus. So in this circumstance, the question has told you which route these are going. So don't just jump in and be like, oxidation reduction, this is negative, blah, blah, blah. It's telling you which way everything is going in the question. Because it means that you're going from VO2 plus to green, which is what, V3 plus, to V2 plus. So you have to look at these redox equilibria, and they've added excess ion as well to this, and see what's happening at each of these stages. So from here to here, it's going from an oxidation state of -2, +4 to +3 to +2. So each step it's being reduced, reduced, and reduced. So that means each step this Fe has to be oxidized every time. So then the oxidation systems we're going to be using is the one with Fe solid in, which is here, and then whatever ones lead to these things, so V3 plus and so forth, right? So then we're going to be using this one, which goes from VO2 plus to V3 plus, and then V3 plus to V2 plus, wherever you are, which is here. And that's actually it. So then you would just describe what's happening here in that sense. So in this case, 4's E value is greater than 2, therefore 4 shifts to the right and is reduced. So you get VO2 plus becomes V3 plus, and Fe solid is oxidized to Fe2 plus aqueous, right? Cool. But that explains how we go from here to here. So that gives you that whatever color they start with, blue to green. Right, but then it says in the question it's gone from green to violet. So if we're going from green to violet, it's V3 plus to V2 plus, which is here. So that means that this has to have been reduced. So that's more positive than this. So then 3 is greater than 2 in its E cell value. Therefore 3 shifts to the right and is reduced, which gives you V3 plus to V2 plus. And then the Fe solid is oxidized and shifts to the left and so forth, and you get that. So that's what gives you that green to violet. So it's really important to just be careful not to dive into this and that, this must be oxidized, reduced. Like, look at the question and it might tell you what it is straight away. Then it says construct an equation for the first color change from blue to green. So all you got to do is just combine them. So from blue to green, we know that this is going this way and then this is going that way, And here we've got 1 electron versus 2, so all you need to do is times this by 2, add them all in, and then like cancel things out. Just for the sake of time, I'm just going to rush ahead and do that. So Fe solid plus 4H plus aqueous plus 2VO at 2 plus aqueous gives you Fe2 plus aqueous plus 2H2O liquid plus V3 plus the 2 of them aqueous. So then it says iron gluconate is active ingredient, some brands of iron supplements, and what they do is then experiment to determine the mass in this one tablet of an iron supplement, and then what they do, and always please flowchart this so you understand what's going on. Don't just dive in and work moles out blindly. The only technique there is to do reverse titrations or back titrations or whatever you want to call it is by reading the question and using your reading comprehension skills that you learn in your SATs. You would be surprised how shockingly bad these kinds of questions are done. So what they've done is they want to look at how much iron gluconate there is in a tablet of an iron supplement. So what they do is they get 2 tabs and they dissolve it in sulfuric acid, right? That's going to lead to what? That's going to give us your Fe2 pluses in this sulfuric acid. And then what they do is they've done it to 250 centimeters cubed. Cool. Then what they do is they titrate 25 centimeters cubed of this solution here. They purposely write it like this so that they make you read the dang question. 25 centimeters cubed of this Fe2 plus stuff is then titrated with this potassium manganate. So KMNO4 has been reacted with it, which its concentration is 0.002. So don't just write titrated and say it again, like it means they've added that. It says the student obtained a mean titer of that. What is that volume? You need to be able to recognize what it represents. People dive in and be like, oh, that must be the volume of this or whatever. And it's like, no, what? Hello? The student gets a mean titer of this. They've titrated 25 centimeters cubed of the Fe2 plus with this. The mean titer is the volume of this, which is why you must do this every time. There's no other excuse, no other way. In this titration, they've told you that 1 mole of manganate, 1 moles of these reacts with 5 of these. So they've told you the ratio of this as well for you. They've told you that the Fe2 plus to MnO4 minus ratio is going to be 5 to 1. This is like literally all you're going to need to work backwards. I'm telling you now. Explain why the student used this concentration rather than the more usual concentration of this in manganate titrations. The only reason that they would use such a dilute amount, so think about it, they're using a more dilute amount. The titer is this. If they use a more dilute manganate solution, the titer is going to be bigger. If the titer is a bigger value, they're using the same equipment, so what it does is it actually reduces the percentage uncertainty. Because percentage uncertainty is your uncertainty over the value times 100, right? Now, if I have an uncertainty of plus or minus 5 and I measure 10, for example, that's 50%, which is horrendous. But if I use the same equipment, that uncertainty is going to stay the same no matter what, as long as I use the same equipment. So all I can do is measure a big value instead. Because if I do that, and if I do 100, then my percentage of uncertainty is now 5%, and 1,000, 0.5, and so forth. So it has less of an impact. In a practical example, if you're 170 centimeters and I do plus or minus 5, you could be 165 to 175. If I then, for some reason, measure you and you're like this tall for some reason, then you're going to be, the range is 169999995 to 170000005. You see the impact is a lot smaller. So that's why to combat percentage uncertainties and reduce them, you can use a much bigger volume or bigger measurement. There you go. And then it says use these results to determine the mass of the iron gluconate in this one tablet, which is why I was saying all of this stuff before, because it's way easier now. Don't blindly work out moles. If you can't justify why, then you're doing it wrong. Now I know that this tablet's got Fe2 plus, which is in 250 centimeters cubed. They took 25 of this, and then it reacted only with this. So I know that this, however much of this is reacted with this, is going to be with this, and they've told us this. Now I know to work backwards, because I know that the moles of the MnO4 minus is going to be its concentration times the volume, so 30.5 over 1,000 times 0.002, which is 2.7 times 10 to the minus 5 moles. Write your units so you know what you're writing. I know that they react in a 5 to 1 ratio, so the moles of the Fe2 plus in 25 centimeters cubed sample, so it makes you force yourself to do that, is going to be 5 times your answer. Right, so that's going to be what? 1.35 times 10 to the minus 4 moles. Then I know that the original tablets were dissolved in 250, so that means 250 centimeters cubed Fe2 plus is going to be 10 times this. So it's going to be 1.35 times 10 to the minus 3 moles. And they're asking you to work out the mass of iron gluconate in one tablet. All of these Fe's have come from the iron gluconate 2 tablets, and they've told you that iron gluconate is this one Fe with all of this stuff. So this Fe, whatever, this gluconate dissociates into one Fe plus whatever the other gluconate part is. So you know that the moles of the Fe is going to equal the moles of the whole gluconate thing, and we have 2 tablets. So all of this came from 2 tablets, so one tablet must have, iron gluconate, the moles of it being a half of this. So the moles of this is going to be 1.35 times 10 to the minus 3, so 1.35 times 10 to the minus 3 divided by 2, which is going to be 6.75 times 10 to the minus 4 moles. Now they want you to work out how much there is in this in milligrams. So all you do is you just do moles times MR of this times the MR of the calcium gluconate. Sorry, not calcium gluconate. Sorry, iron gluconate, which is this. Sorry, we say the calcium gluconate a lot in medicines. I'm so used to saying it. Which could be 445.8, which is 0. Let me work that out, times 445.8, which is 0.300915, which is roughly 0.301. But remember that we want it in milligrams, this is in grams, so that would be 301 milligrams. Now it says some of these contain iron 2 sulfate and iron 2 fumarate. Use the information in this table is taken from the two supplements. Iron supplement here has got FeSO4 and it's got a massive iron compound in this one tablet is that, and then the iron fumarate is this, and it's got a massive iron compound of this. It says which one would provide a greater mass of iron per tablet, right? So you could just sort of figure. So what you've got to do is you've just got to work out the mass of the iron in this, right? We know that there's 180 of this iron compound, right? So the moles of this iron compound is going to be so the moles of, for example, iron 2 sulfate would be 180, but remember in grams, so 0.18 divided by the MR of this whole thing, right? So that's going to be what the MR of FeSO4 is. And I'll tell you how many moles of this whole thing is. Now they've told you that there's FeSO4, so 1 Fe in every single one of these. So that's going to equal your moles of your Fe. Then you could work out the mass of the Fe using this times the MR of the Fe, which if you do all of that just to rush ahead, gives you 66 milligrams. And then the same thing for the other one. If you do the same technique, you get 69 milligrams. So then you get B has more within the tablet. I'm just skipping ahead just for the sake of time. Sulfuric acid is an important chemical used to make detergents, fertilizers, and dyes, and it's manufactured in a multi-step process. In the first step of the manufacture of sulfuric acid, sulfur dioxide can be made from the combustion reaction of hydrogen sulfide as shown in this reaction. Explain why the enthalpy change for reaction 1 has a negative value. Use ideas about enthalpy changes associated with bond breaking and bond making. Bond breaking is endothermic because you've got to put energy in to break bonds. Exothermic is the opposite, so bond making is exothermic because energy is released when making bonds. So when you're reacting this and this together, what you're doing is you're breaking down their bonds within them and then combining them to make new combinations of bonds, right? So if the overall enthalpy change is exothermic, it means that there has to be more energy that was released breaking them than was put in to break the bonds. So you say more energy is released making bonds than is needed to break bonds. So if it says some standard entropy changes are given below. Using calculations, explain whether reaction 1 is feasible at 20 degrees Celsius. So delta G is what we're going to use, and that is equal to delta H minus T delta S. So list out what you have so far. So we know that delta H is going to be minus 1125 kilojoules per mole. We know that T is going to be, so it's 20 degrees, but they want it in, this only works in Kelvin, so you're going to have to convert that to kelvins by adding 273. So the temperature there is going to be 293. And delta S is what we need to find out. So delta S is equal to S end minus S start, as in the entropies. So in this circumstance, it would be 2 times 248 plus the H2O, there's 2 of them, so 2 times 70, all minus the entropy at the start, which was 202 times 206, plus 3 lots of 2O. That gives you an entropy change of minus 391 joules per Kelvin per mole. Now, in this here, this enthalpy change we worked out from before, that's in kilojoules per mole. This is not consistent, like the units are different, because this is in joules and that's kilojoules. So in order to make this work, we have to convert this down into kilojoules, or change the other one into joules. So then I'm going to convert this to kilojoules, so that's going to be as minus 0.391 kilojoules per Kelvin per mole. Now we have all the information to work out delta G. Delta G is going to equal delta H, so minus 1125 minus temperature 293 times delta S, which is going to be minus 0.391. If we do that, we get minus 1010 kilojoules per mole. And the question is asking if it's feasible or non-feasible. Well, it's feasible because delta G is less than 0. So now it says calculate the standard enthalpy change of reaction of hydrogen sulfide using the enthalpy changes for reaction 1 and the standard enthalpy changes of So the examiner report for this question says that a lot of people fumbled it and did not introduce the correct cycle. Whenever you're doing enthalpy changes, you have to do Hess's law cycles. There's no other way around it. I don't care who you are, what you can do, what you're capable of. The only way to do it is through this. Now, when you're doing this as well, you cannot tell what the cycle's supposed to be based on the question text alone. You can't just read it saying enthalpy of formation and immediately conclude it must be, like for example, elements and going up like this. It doesn't work like that. And if you're doing it like that, you're objectively doing it wrong and need to stop. When you're doing this, you need to identify what the overall enthalpy change is that they want. So they want you to find the enthalpy change of formation of hydrogen sulfide using this enthalpy change for this reaction 1. Now, whenever you do this, always write out what is the actual, what the actual reaction is that they want you to find. They want you to find the enthalpy change of formation for hydrogen sulfide. So the enthalpy change of formation for hydrogen sulfide, the definition says it's where you make 1 mole of a substance from its constituent elements in their standard states under standard conditions. So that's going to mean that you're going to make 1 here of H2S gas from its elements in their standard states, which is going to be H2 gas plus S solid. Now every single Hess's law cycle in the universe, every arrow has an enthalpy change on it, so we need to label what this is just so we know what we're actually doing with it. And that is your enthalpy of formation. Cool. This is your overall reaction, and then you're going to decide what goes down here. And the only way to know what goes down here is by looking at the table and figuring it out. There's no other way to tell by reading the question, like the text. You can't say, oh, it's formation because that's what they want us to find using what they've given us. So what I mean by that is to look at the table and see what the enthalpy changes they've given are, and then relate it to what you have. Here, it says this is the enthalpy change of combustion. The enthalpy change of combustion is where when you're combusting 1 mole of a substance completely in oxygen to form its combusted products, right? So here, these are the enthalpies of combustion, which means these are all being combusted into the combusted products, which means they're on this side of the equation. Compare this to what you've got here. So one by one, look at them. So this is H2 gas, this is also H2 gas, which we have the enthalpy of combustion for, which is where you go from 1 mole to combusted products. So it means I probably could write maybe down here, combusted products. Then the next one, right? Here, sulfur solid. That's the 1 mole on this side. So I could probably write combusted products too. Cool. And then they've given us another enthalpy change here, plus this, gives you those two. If you look closely, that is the enthalpy of combustion because you're adding it with oxygen. And this is in its, to get its standard state. So then we can add the arrows on by looking at them one by one as well. So don't just immediately jump up and down and this and that. Use your common sense. H2 gas, enthalpy of combustion, combusted products. The arrow's got to go this way. And the number, label it, is going to be minus 285.8. Here, we're going from sulfur. Here's sulfur, 1 mole, combusted products. So that means the arrow is going down, and it's going to be minus 296.8. Here, and here, it's being combusted, so it's going down as well. And also, the definition says it's when it's 1 mole of a substance, combusted blah 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 to make its combusted products. Here, this is 2 moles, so we actually have to do a half of its enthalpy change there. Because this is 2, but we only have 1, so we're going to have to half this now. Remember how I said every arrow is an enthalpy change, so that's why this has to be done this way. Now Hess's law says that as long as you start and you finish at the same point, the enthalpy change will be the same. So that means as long as I start here and finish here, no matter what route I take, it'll be the same. So I could go down here and then back up here, and it will equal this. So you would write that. So you'd say delta H of formation equals, and then go down, and when you follow the arrow, you put the same sign. So minus 285.8 minus 296.8, and then here we're going against it. So minus a half and then minus 1125, or alternatively you could do just like plus a half 1125 or whatever you want. Now if we do that, we should end up getting, I'm actually going to lose my mind, minus 20.1 kilojoules per mole. If you do it like this, you'll never get it wrong ever, unless you write it wrong in your calculator or something. Now the second step in the manufacture of sulfuric acid is the conversion of SO2 into sulfur trioxide using this equilibrium, and an industrial chemist carried out some research into this. They fill this many deciliter container with this at room temperature and 12 grams of O2, and then they add vanadium oxide, heat the mixture, and the mixture is allowed to reach equilibrium at a pressure of that and a temperature of that, and the sample of equilibrium mixture is analyzed and found to have this much. First step says write an equilibrium for Kp for this equilibrium, and then include the units. So we're going to write the partial pressure of SO3 squared, all divided by the partial pressure of SO2 squared, times the partial pressure of O2. Now it's units. You can't do anything with pascals here, because here, where is it? Atmospheres? It says allow pascals, well, you should try and stick to what they've given you in the question, right? So that's going to be atmospheres squared divided by atmospheres squared atmospheres, which is the same as saying atmospheres squared over atmospheres cubed. Now when you're dividing things like indices, so for example if I do 2 to the 4 divided by 2 cubed, that becomes 2 to the 1. And that makes sense, because if 2 to the 4 is what? So 8, 16 divided by 8, which is 2, which is the same as 2 to the 1, right? If I do 2 to the 4 times 2 to the 8, that's the same as saying, well, you add these two together, so it's 2 to the 12. So whenever you're dividing powers, when like this and this, and they have the same base, you can take away the powers. So in this case, it's atmospheres 2 divided by atmospheres to the power of 3, which is going to be atmospheres to -1. Now, there's only one way to do equilibrium calculations, Kc, Kp, K whatever, Ka as well. You need to figure out what you have at equilibrium, because it's not going to be the same as what you start with. And a lot of people fumble this because they don't read the question properly. This question has told you that we have this as our overall equation, so rewrite that. And it says they filled this decimeter cubed with SO2 at room temperature, and then they add 12 grams of O2, right? Now what they do is they add vanadium, the catalyst, and they allow it to reach equilibrium, and then at equilibrium it has this much. So remember that you have your initial moles where you're starting things out, and that's before equilibrium, and then you will have moles at equilibrium, or the end of a reaction, and this will be your change in moles. It's really important you do it that way, otherwise you're going to fumble this and get it wrong. Think logically what's happening. They're mixing, whatever, this together, right? And then this is going to react with this is going to go down a certain amount, that's going to go down a certain amount, that's going to be up. So we need to put what we know in. So in this question, we need to know what the moles of this is. Now they've told you it's at room temperature and pressure, so that means you can use the moles equals volume over 24. So the moles of the SO2 is going to be 10.2, its volume, over 24, which is 0.425 moles. And then the O2, they've told you, is 12 grams. So then this one's is going to be 12 over 32, which is 0.375 moles. Before they've set this equilibrium up, and they've just mixed everything together, there is none of this. It's 0 at the start. Then the question tells you, at equilibrium, it has this much SO3. So at equilibrium, we have 0.350 moles of this stuff. Its change has been plus 0.350. If this has gone up by 0.350, whatever is in a 1-to-1 ratio with this, so here, will have dropped by that much, because every 2 of these makes 2 of them. That means we will have lost 0.350 of this, but because this is every one of these makes 2 of these, this will have dropped by half as much. So that means this will have dropped by 0.350 over 2, which is 0.175. Now, at equilibrium, the moles of each thing is going to be, this minus this. Well, so, 0.425 minus 0.350. So if we do that, we get 0.075. And then for the other one, the same thing, we get 0.2. Now, they want us to work out what Kp is, so we need to work out some partial pressures. So partial pressure is equal to your mole fraction times the total pressure, right? So in this circumstance, what the fuck? So this is Kp, which is the equilibrium constant for pressure equilibrium. So we need gas equilibrium, sorry. So we need to work out the partial pressure. Now the partial pressure is equal to your mole fraction times the total pressure for each gas, because each gas will exert its own partial pressure. So we know what the total pressure is, because it told us in the question, 2.50 atmospheres. So total pressure is 2.50 atmospheres. So we need to work out the mole fractions for each of them. And then, hence, the partial pressure. So I'm just going to jump ahead and do partial pressure together in one go. So the mole fraction is just going to equal the moles of whatever it is over the total, right? So the total moles here, if I just write there, is going to be 0.075 plus 0.2 plus 0.350, which is 0.625. So the mole fraction of each of these is going to be, for example, the first one is going to be 0.075 over 0.625, and then we're going to times it to work out its partial pressure by the total pressure, which is 2.5. In here as well, 0.02 over 0.625 times 2.5, and then 0.350 over 0. Now if I do that, I end up with partial pressures of 0.3, 0.8, and then 1.4 for each of these. Now Kp is what we've just written here, and all you do is you plug it into the equation that you've just made. So I'm going to just do it over here just for the sake of space. So that's going to be your SO3 squared, so 1.4 squared over 0.3 squared times 0.8. Okay, so the chemist repeats the experiment and be at a different temperature, and they found that the value of Kp is greater than the answer there. So explain whether this temperature is in second experiment is higher or lower. So if you look here, if the Kp's gone higher, that means that this has gone up and these two will have gone down or something like that. So it means the equilibrium will have shifted to the right. So you would start by saying that. So a greater Kp value indicates that the equilibrium shifted to the right. Right, now look at this here. This is an exothermic direction in the exothermic direction. Now thinking of it logically, Le Chatelier's principle says that whatever you do to an equilibrium, it'll counteract the change, right? If this is going in the exothermic direction, what that means is it's trying to increase the temperature. So the change it's opposing must have been us decreasing the temperature. So therefore, it's a lower temperature because the forward reaction is exothermic. Then it says, explain the significance in this Kp expression being greater than 1. So if we look here, this is a fraction. Any fraction that's bigger than 1 means the top number is bigger than the bottom. For example, if I do 4 over 2, that's 2, right? But if I do like 1 over 2, that's 0.5. Whenever the top number is higher than the bottom, you have a number bigger than 1. So in this case, they've told you that the top number is bigger. And if that's the case, that means the equilibrium is more to the right. Yeah, because there's more of this than this, and that makes sense because that's higher than the bottom. So that means the equilibrium is to the right. So now it says vanadium oxide is used as a catalyst in this equilibrium, and then here we have it, and it says explain how the presence in this increases the rate of reaction. Include a labeled sketch of the Boltzmann distribution on the grid below and label the axes. So on your y-axis, you're going to have the number of molecules. On your x-axis, you're going to have energy. Now no particle has no energy in this circumstance, but then it starts to get higher and higher and higher, and then lower and lower and lower, and then it levels off. It doesn't actually touch the x-axis at very high energies. And then as well as that, you've got to have an energy where, you know, the reaction starts, the activation energy, so that could be like anywhere here. So all of these particles above it have more energy, you could just read the axes, than the activation energy. So then it says here to include a label thing here. Two ways around it. You could just describe it, or you could draw physically like an activation energy, for example, there. Either's fine. So we've got our axes, we've got all of that bits, so let's actually write what it says, because it says explain how this increases the rate of reaction. Now, every single reaction in the universe depends on two things. They depend on, 1, a collision in the right orientation, and 2, having the activation energy. If you max out these two, then the rate of reaction goes higher, because more of these are happening. So then, in this circumstance, it's told you how the catalyst is working, right? So that means that it's going to lower the activation energy, which means, and here you should use this diagram to explain what that means, because if I draw the activation energy here now, you can see there's loads more particles that have enough than before. So it lowers the activation energy, meaning that an increased proportion of particles or reactants have enough energy to react. Therefore, you get an increased frequency of collisions leading to reaction. There you go. Explain whether vanadium oxide is acting as a homogeneous or heterogeneous catalyst. So let's go back to a question and see if there's any hints on what might tell us. So it's told that you're adding this as a catalyst, and it says explain how this here increases the rate of reaction. Gas, 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 solid. So it's clearly a heterogeneous catalyst. We need to say why. It's a heterogeneous catalyst because it's in a different phase to the reactants. There you go. Okay, so this question is about weak acids, and the Ka value of these weak acids is shown in this table below. Cool. So it says calculate the pH of this much C2H5COOH, which is the propanoic acid. And it says give your answer to 2 decimal places. So we're dealing with a weak acid, which means we're going to have to use Ka, because eventually to find a pH in any scenario you need H plus as concentration. So our options are to use Ka equals H plus A minus over HA, or Ka equals H plus squared over HA. Now, it's important to remember that weak acids, the equilibrium is so far to the left that there's barely any A minus. So if there's enough A minus to warrant using it in a Ka, that means there is salt present. So whenever you see this, it means there's salt. In this, they're asking you to find the pH of only just this acid with no salt in, so that's the one we're going to use. So we're going to rearrange that to get H plus. Always write your working out first, rather than, you know, jumping around with numbers and saying all kinds of garbage. Rearrange the equation, write your working out first, then put the numbers in. So Ka times HA would equal H plus. So if I square root that, I'll get, sorry, H plus squared. If I square root that, I'll get H plus. So H plus is going to equal its square root of the Ka, which was 1.35 times 10 to the minus 5 times H plus, sorry, times HA, which is 0.08. If I do that, I get 1.039 times 10 to the minus 3. And pH is going to be negative log to the base 10 of the thing you just worked out, the answer, which is going to be 2.98. So student adds a total of this much NaOH to this much and monitors the pH throughout. Show by calculation that this much is required to reach the endpoint. So the endpoint is when all of the acid has been neutralized. So what you should probably do, and you must always do, is write a quick equation, just a very quick sketch of what is going on. So an acid plus a base, acid plus a base makes a salt plus water. You're going to work out the initial moles and the moles after reaction. We don't even have to do that, to be honest, because we just need to work out how many moles we need to react. So what I mean by this is that if we work out the moles of acid, it's going to be the acid volume times concentration here. So it'd be 25 over 1,000 times 0.08, which is 0.002. Now, if we're going to reach the endpoint, how much base we're going to need is also going to be 0.0002. Sorry, too many zeros. So that means moles of base you need is going to be 0.002, and they've told you what the concentration of this is. So if N equals CV, then V equals N over C, which is going to be 0.002 over its concentration of 0.1. And if you do that, you end up with 0.02 decimeters cubed. But they wanted centimeters cubed, so to divide that, you times by 1,000, and you end up getting 20 centimeters cubed. There you go. And here, a lot of people fumbled this because they just wrote lots of random sums and figures without a single word to describe what it says. That's what it says word for word in the exam report. Candidates should remember to provide written indications of what they're working out. Presenting calculations without any annotations can make it harder for error carried forward marks to be given. So please write your working out, and this is what I mean. So before, I said that write this out. Write it for any acid-base reaction in the world. Acid plus a base makes a salt plus water. Right? And then what you're going to do is you're going to work out your initial moles and your end moles, and use that to then eventually find the pH, because you need to figure out what's happening in this reaction. The initial moles of this we worked out before was 0.002, right? Now, the moles of OH minus, because it's the final solution after they've added this, is going to be, where is it? These two times together, so 45 over 1,000 times, what was its concentration? Sorry, 0.1, which is going to be 0.0045. At the end of the reaction, just use your common sense. This is reacting with this. If they react, this is going to go down. This is going to go down. These will go up. Now, if we do that, the amount of acid we have left is going to be 0. The amount of base we have left is going to be this, taken away from that, which is going to be 0.0025. We'll have 0.002 of this salt. We don't care about the water. It says to find the pH of it, so pH is eventually going to need to culminate in you finding this. What's left in this, there's no HA, so you can't use Ka anymore because there's nothing there. There's only OH left. So you should think, what do I know that links H plus and OH? Kw is linked to H plus and OH minus. We only have the end moles, we need to find the end concentration. So the concentration of OH minus is going to be this is 0.0025 divided by, it's the new volume of the solution, which is 45 plus 25. So that's going to be 70. So it's going to be 70 times 10 to the minus 3, or 70 over 1,000, which gives you 0.0357 moles per decimeter cubed. Now, Kw equals this. We want to find H plus. H plus is going to equal Kw over OH minus, which is going to equal 1 times 10 to the minus 14 over 0.0357, which gives you 2.8 times 10 to the minus 13. Then the pH is going to be negative log to the base 10 of your answer, which is going to be 12.55. That's how you do it. Any question like this, just write this out so you can help yourself logically work out what's happening, and then the rest is quite easy. So now it says on the axes below, sketch a curve for the pH changes of the addition of this to this, right, during the addition of those two. We worked out how much volume there was for neutralizing, so our equivalence point is going to be where this volume is 20, and we're going to be done at 45 with this pH. So all you got to do is just draw that. And they've also told you to work out the pH at the start. So the first pH we started is at 2.98. So 1, 2, 3, 4, 5, 6, 7. So it's going to be about what? 1, 2, 2.98 there. We know at 20 it's been neutralized, so our vertical point is going to be here. It doesn't always mean it's at 7, it's vertically there. We know that our end is going to be what we just worked out, 12.55. And we know that's after 45 has been added. So 45, we would put a 12.55, what's it, 14, 13, 11, 12.55. So we need to link these two together. Where's the other one gone? Come here. Like that. So what you would do, and you have your vertical equivalence point here. So all you got to do is just draw it like that. So then all you do is you would, as best as you can, try to anyway, like that. As best as you can, trying to draw it. Now it says the student considers these 4 indicators, which one would be the most suitable. So an indicator, remember that this here, halfway across this vertical point, which I've drawn horrendously, is going to be where the actual neutralization part happens. We need an indicator that changes just where this happens, so that if you were to add a bit more, it would change color, and a bit less, it would change color. So whatever lies within this vertical equivalence point is ideal, the narrowest we possibly can. That way, even the teeniest amount above it can help change color and, you know, find out what we need. So we need to find out whichever one fits this pH range that we care about. So in this case, no, that's too low. No, that's too low. Yes, and no, that's too high. So Cresol purple, or whatever it's, how you ever pronounce that. So Cresol purple, but you need to say explain why. Because its pH range matches the vertical section. There you go. So then the student repeats this experiment, starting with this much HCN and then adding this much NaOH. Predict one similarity and one difference between the pH curve of these two. So the similarity is that, you know, I mean, first of all, this is still the same number of concentration of volume, and this is still a monoprotic acid. It only puts 1 H plus out for every NaOH. So that means you're still going to have the equivalence point being, you know, the neutralization, sorry, going to be the same volume of NaOH. So the similarity is both require, because it's what determines how much you're going to need is the moles of this stuff, remember, because these two are reacting with each other. We measure things like that in moles. So both require 20 centimeters cubed NaOH. But then what's the difference? What's the difference? The difference is going to be, well, if we can see, look back in the question, maybe there's some clue here. It says hydrocyanic acid. Make sure you use the whole question. It's told you that this hydrocyanic acid, its Ka, is this 6.17 times 10 to the minus 10, whereas this is bigger. So this Ka is bigger, meaning it will have, this Ka is bigger, this one's lower. So K, remember that we said Ka equals H plus blah blah, so H plus is the square root of K times HA, right? Now if we look at this, the concentrations are the same, the only thing that's changing is this. So this Ka is going smaller, that means the amount of H plus is going smaller. So if there's less H plus, the pH is higher. So then the difference is that HCN starts at a higher pH. You make sure you use the whole question to make sure to, you know, when you're answering these things, because it's all in the question. They're not expecting you to mysteriously know what, you know, like, you know, the pH of starting pH of HCN is, or its Ka. The student calculates the pH of this much HiO3, and they assume that the equilibrium concentration is the same as that. The student measures the pH and finds that the measured value is different from the calculated value. Explain why the measured pH is different from the calculated pH. So clearly, remember that every acid in the universe does this. Now, before I said that you could do Ka is roughly H plus squared over HA, because in weak acids the equilibrium is so far to the left, there's barely any of this going on, right? However, they've just told you in the question they measure the pH and it is different from the calculated pH. So clearly that's not working anymore, which means it must have dissociated enough for this to be a thing. So therefore that's what you would say. So it must be that it must be a stronger weak acid and has dissociated more. And this dissociation is not negligible. Because usually we kind of assume, oh, it's so far to the left, there's barely any of this, that's why this works. But clearly if that's not worked, this doesn't hold. So then it says 3 students carry out a rates investigation on the reaction between bromine and propanone in the presence of hydrochloric acid. Each student investigates the effect of changing one of the concentrations of the reactants while keeping everything else constant. And here's their results. So we just have a look, remember, we're looking at the concentration against time. We can see the concentration against time is falling down. And this is with the initial rate against concentration of this. And that's just going up. And there's not like a curve or anything, so that means the steepness of the gradient is constant, steepness of the gradient is constant. Now, it says, explain how the reaction orders can be determined from these results and then determine the rate equation and rate constant. So we need to look at things with regards to each piece of data one by one. So we don't just jump in and sort of go left and right and look at everything. We're going to do it bit by bit. So if we look at like student 1's results, let's look at that graph first. So they've told you on the y-axis it's moles per decimeter cubed. When you work out the gradient, you're doing the difference in y over the difference in x. And remember, gradient is the same as just saying the word steepness. Right? Now, if we're dividing y over x, the change in y over change in x, we're dividing their units, which if you do that, gives you moles dm minus 3 s to minus 1. For example, if I have distance and time the gradient of this is going to be the change in distance over the change in time, which is velocity. Speed equals distance over time, or speed. So the gradient can help you work out constants. So that means here that this gradient is the rate. Now, look here, the rate is the gradient, which is also steepness. The steepness is constant, so the gradient is constant. So here, the gradient is constant, which means the rate is constant, despite what's happening. BR2 is dropping over this reaction. BR2 decreasing. Therefore, the order with respect to BR2 is 0 order. Because if the steepness was changing and becoming, can you see how it's very steep here, less steep, and less steep? You can see that the rate is decreasing as the BR2 is dropping. But here, it's fixed, it's staying the same. So no matter how much BR2 you have, the rate is constant. So therefore, it's 0 order with respect to that. So we've actually figured that part out. Cool. This one's different though, because it's saying initial rate against this. There's not really a gradient that helps here. We don't really understand, you can't do the thing I did before. But you need to think about it logically. The initial rate is the rate that they're working out straight away, and they're changing the concentration. You can see that as the concentration is increasing, the initial rate is increasing. And it seems to be by the same amount every time. So from here to here, it's the same. The change is the same. From here to here, the change is still the same. So that means that it's increasing a set amount every time, with every increase of this. So that could suggest that it's first order. Now, as well as that, if we have a quick look, there's no changes here, and the only thing that's changed is H+. So because this is increasing by the fixed same amount every single time, because the steepness, the change in, y, but the change in x is the same, that must mean that it's first order with respect to that. So then the second one, you would say student 2, is that the rate is proportional, because it is, it's one straight line through the origin, it's proportional to this, the CH3, CO, CH3, which means that the order with respect to this is first order. But then as well as that, we've got the table at the bottom, so student 3, let's compare theirs now. So with student 3, the only thing that changed between these two experiments is that they doubled this. We can see that the rate has gone up by whatever that is divided by that. So 2.5 divided by 1.25 is 2. So you would say 2 times the concentration of H plus led to a 2 times the initial rate. Therefore, the order with respect to H plus is first. So now we know that this is this is first order, that's first order, and that's 0 order. So now they said determine the rate equation of rate constant. So rate equation is going to be rate equals K times the concentration of H plus times the concentration of the other CH3, CO, CH3. Now they want you to work out the rate constant, which is going to equal the rate over the concentration of H plus times the CH3, CO, CH3. If I do that with the numbers, if I just pick like equation 1, it's going to be 1.25. Like you see, it says times 10 to the minus 5. Don't get caught on that one. Times 10 to the minus 5 over, where are we? 1.6 times 0.2. So 1.6 times 0.2, which is going to equal roughly 3.906 times 10 to the minus 5, roughly 3.91 times 10 to the minus 5. But then they also want you to work out its units. So we've got the number, we want the unit. So the rate is going to be in moles per decimeter cubed per second, and so all rates are measured in. And here it's going to be moles per decimeter cubed, moles per decimeter cubed. So it's the same as in this squared. Now that's like saying mole 1 dm minus 3, right? So we're going to rewrite this to a nicer form. So moles dm minus 3, s minus 1, all divided by, well, if you're timesing moles by moles, you're going to get moles squared. dm3 times dm3, add the powers together. So you're going to get dm minus 6, and there's no s there. And then that's like saying mole 1, so mole 1, 1 minus 2, moles to the minus 1, minus 3 minus 6, dm cubed, s minus 1. There you go. Thank you very much. I hope that helps. Please like, share, and subscribe. And sorry if my voice sounds very fluctuant in all these videos. I don't know what's happened. I kind of got ill. I'm fine. I'm better, but my voice is just still tweaking, and it just seems to be every video I'm like losing it. So, yeah. Thank you.